Looks like we're about ready to get started. Welcome back, everyone, so far. And that's about close enough. Welcome back, everyone. So we're nearly done with the section 11.8 on power series. And this one right here, we're not going to try to race through this one. I believe we're probably more likely going to be finishing the 11.9 section when we come back on Monday's class next week. So what that means is 11.8 is going to be the very likely last section that's going to show up on exam 3. Dealing with power series, there's 3 different kinds that can come up as according to this trichotomy right here. So depending on how the exam looks, I'll try to be very careful and mindful that part 3 is a bit of the longer one. These ones are a little bit quicker, but it could be one of the 3 that could come up. But that's where we're at so far, running through power series. This is our first really big shift in chapter 11 when every series that we were dealing with and sequence we were dealing with never had the variable x in it. Kind of weird when you think about it, but for the very first time now in power series, we are dealing with a variable x. So conditions on convergence involves now solving inequalities involving x. We're on the very last problem to take a look into, but any questions or comments first, folks, before we get started? Okay, let's jump in. So we are on this problem right here. And it's kind of an unusual one compared to the last ones that we're looking into. We have 2n factorial versus an n factorial in the numerator. X power of n tells us that the center on this one is right at 0. Always a good idea to think about the center, so let's write that in before we analyze it too much further. So that part indicates center is a is 0 for that particular power series. And this is a hard one to guess what might happen on. There's n factorial in the numerator, 2n factorial in the denominator. On one hand, it might feel like a type of balance between the two, where we might be in, say, case 3, a limited domain on which it converges on. But actually, this one turns out to be either case 1 or case 2. One of them is going to win outright. If it's n factorial, then that would mean the whole thing has radius 0. The interval would be I, which would just contain the center right at 0 itself. But 2n factorial, if that one's growing way faster, it would be case 2 instead. The interval of convergence will be in the entire real number line, which says this always makes sense as a number. Way to test it is really just a ratio test on this thing. This will be like the 4th ratio test we've applied in this section. We'll call this summation an. Cite the ratio test and start analyzing from there. And the ratio test, this is our pattern that we've been maintaining for just about every single time we used it. We need the nth term that goes in the denominator. The n plus 1th term goes into the numerator. And we find it by replacing n by n plus 1. So we have n plus 1 factorial above divided by 2n factorial below. And don't forget x power n plus 1 as well. Then just take all that stuff, throw it together in the limit. This will be a limit as n goes to infinity. We can hide that for just a moment. Of an plus 1 divided by an. Now, just another one of those limits, probably maybe the 12th time we've done the ratio test at this point. This becomes limit as n goes off to infinity. Take just that entire structure right there. Oh, looks like we've got a chat. Oh, the 2n. Let's see here. Oh, yeah, for putting in n plus 1. Thanks for mentioning that, Brian. then that'd be 2n plus 1. So 2n plus 2 factorial right there. I think a couple people in class saw that simultaneously. So 2n plus 1 as a factorial there. That was going to give us a weird result. Thanks for spotting that error, folks. And now taking this whole thing, you know that 2n plus 1 factorial is complicated enough to want us to maybe pause a little bit longer right here. Let's actually simplify this down a bit. N plus 1 factorial was going to simplify as a n plus 1 times n factorial. Factoring being the technique, we'll factor this one as well as x by x power n. And that's now a 2n plus 2 down below. So 2n plus 2 factorial. One last step. The 2n plus 2 factorial can potentially also factor in a nice way. Let's go n plus 1 n factorial, x times x powered n, starting to get complicated on that numerator. And then the denominator, recall, we're going to divide by an, which will eventually involve 2n factorial. So if we go here and make a 2n factorial just show up, we'll have an awesome cancellation as well. So let's start factoring the factorial as 2n plus 2, 2n plus 1, 2n. Next factor would be 2n minus 1, 2n minus 2. But if we just tie it off with a factorial, we have all of those remaining terms off to the right. So big simplification right there because of that omission. Gives us all that stuff. And here's where it drops in. N plus 1, n factorial, x times x powered n, all over 2n plus 2, 2n plus 1, a little bit longer on that fraction, and 2n factorial. So didn't look like it would blow up that much, but with factorials everywhere, it just becomes a lot of stuff on the next step for the successor term. Now we divide by this, so multiply by the reciprocal. 2n factorial is now above n factorial times x power of n. Finally, we've got it all together. The cancellation phase is pretty big on this one, but the bigger danger is to accidentally leave something behind. So let me know if it looks like I'm skipping anything there. N factorial diminishes or just vanishes. 2n factorials vanish. X power of n is gone. It looks like just 3 pieces is left. 1 factor in the numerator, 2 factors in the denominator. No further cancellations. And so now we have right here, let's use this trick that we've been using all along. Absolute value is going to solidify right on the one part that could be negative, which is x. But x can come clean outside because it's a constant regarding to the limit as n goes to infinity. If we're dealing with a limit as n goes to infinity, the only stuff that's trapped inside are things indexed by n. So all that stuff's still there. Oh, also the n plus 1. Somehow I actually missed that part. Hang on, doesn't that cancel? We have an n plus 1 here. Could factor out a 2, and that's also an n plus 1. There's more cancellations than meets the eye. This cancels with this, leaving behind just a 2. That's kind of nice in a way. The more you can cancel, the easier it is just to look in the limit and evaluate it. So that's worth taking time on. So now left over is limit n goes to infinity. Our x has pulled out an absolute value, so that part's accounted for. It looks like it's just 1 over 2 times 2n plus 1. And honestly, if you didn't do that cancellation, you would have had the same conclusion over here. It would have been degree 1 over degree 2. But now it's degree 0 over degree 1. Same conclusion. This limit is 0. It turns into absolute value of x times the value of the limit, 0. That means the whole thing is now just 0, which is less than 1 for all x. X had nothing to do with convergence this time because the limit itself outputs a 0, just wiping out x. That's kind of nice. If this happens, what we'd want to do next is cite the ratio test again. We are in outcome I. Our limit is 0, which is certainly less than 1, which means we have absolute convergence. And this absolute convergence happens now for all x whatsoever. So we can now just conclude and say summation an converges for all x implies we really are in case 2. Converges for all x means radius is infinity and interval of convergence goes negative infinity to positive infinity. So that'll be the last thing we state. Radius infinity says, well, that can only happen if the interval I is negative infinity to positive infinity. We state this because it's just a reminder that's the domain of the function defined as a power series right up here. But we did it. This one is finally, I think, the first time case 2 came up, or double I, however you prefer to say it. Any last questions at all, folks, finalizing this one? Okay, it's definitely pretty abstract stuff, and we have constantly been saying this is now a mathematical function. We're really verifying that the moment we say we have an interval of convergence, that's the domain. And because we used the ratio test, when we said convergence, we have strong convergence. This is absolute. Convergence. So that means this takes on a value for every x you pick. It'll converge to a real number, and that will be the unique output to the mathematical function. Lots of weird stuff going on, and that's what section 11.9 is all about. Representing ordinary functions like, say, arctangent natural logarithm, like this through a power series. It's a first start into Taylor series, Maclaurin series, which is going to pick up in the next sections. So think of 11.9 as a slow build to those end methods in chapter 11. So let's take a look into those new methods next. Here's how it goes. One thing that's kind of weird about this is it starts with the geometric series out of nowhere. And it's a weird use of the geometric series. Let's take a look at it from our list of notes right here. Our ordinary geometric series is indexed at 1 and goes off to infinity. And the power here is n minus 1. But if you re-index that by setting this down 1, the power on R has to go up 1. And that's what we see. Index is down at 0. X plays the role of R now this time. And n goes up by 1. So this is re-indexed at 0 for what feels like kind of an inexplicable reason out of nowhere. But it's just because now that we're in power series, this is the natural starting point for a typical power series. By the way, this one would be called a Maclaurin series in the upcoming sections because the center of this one is 0 as well. So the geometric series, let's cite this right on the problem just so we can get a better view of what's going on with our new format. So here's the old statement of the geometric series. We can tie this together with a new theorem. It really helps the brain out to see just what in the world is going on this time. So taking a really strong look at this, big feature is how does the geometric series converge? R has to be less than or equal to 1 in absolute value. And over here, we're told that this geometric series converges to 1 over 1 minus x, and this is just the sum listed out, if absolute value of x is less than 1. That's our tie-in. So absolute value of x is playing the role of absolute value of r. So think of x literally as r this time. So if that's the case, we have from here, x power of n is matching this part. We're ignoring the a value completely in the formula for the geometric series, but that would just then mean a is a 1 right up here. If this x is a r, you could put an x right there, and that ties in the 1 divided by 1 minus x. So that's what's going on between the two right here. Feels incompatible, but the things that happened was re-indexing is the first thing. Second thing, x is r, that's interesting. And the third thing, the value a in front of x is just totally missing. That's why the numerator is a 1. Any questions at all, folks, with that view of this new formula through the geoseries? Okay, taking a look into all that, now we're ready to start using this right here. I'm going to screenshot it in this kind of way. But also what this theorem is also saying is, it's known that the function f of x equals 1 divided by x minus 1, hang on, that looks like a typo, let me fix this. 1 minus x is what that should actually read as. Sorry for the random typo out of nowhere. This function, which turns into this, which terms could be listed out in this way, is represented by that power series. And if we go with that representation, our domain is a little bit short. It's from -1 to +1, but that definitely is a domain. Let's write out one more thing. We're going to go for interval of convergence. This gives us a radius of convergence 1, from which you get the interval of convergence down here from -1, +1. If this was absolute value x less than 5 in a different problem, intervals from -5 to +5. So let's give this a try then. Our goal now is to take a random function like this one down below, force it into this structure, and represent it this way as now power series. We'll also state the interval of convergence, which makes sense because we want to know for what values of x does that power series representation even make sense. It's not always a large value, at least not in these notes here. Well, let's give this a try then. Here's how it goes. The idea is we need to, like we said, in a very contortionistic way, force this function to look like that, not by breaking algebra, but by valid algebraic manipulations. Very first thing we want is a 1 in the numerator, so we meet that already. Next thing we want is a 1 right there, so that suggests we should change the order of the terms in that denominator. The 1 over -4 plus x, still not there. We want the 1 highlighted down below. Actually, let me just highlight this way. This is our big want. We're always looking at this part to match it up. We can get that 1 just by factoring out a -4 from the denominator. Factoring out a -4 in the denominator looks like this. -1/4 times 1 over. Here's the 1 we wanted, so we've matched up that 1. And we factor out a -4, so that leaves negative x over 4. Checking the format, we have exactly what we want. Over here, it's 1 over 1 minus x, and we place x to a power n. Whatever this is, no matter how weird it looks, it's now playing the role of that x down below right there. Here's where we make a huge change in the format. This x goes in there in the power series. So let's do that right away. This becomes a summation from 0 up to infinity of take everything to the right of the negative sign, which is exactly what we did here in this formula. This is going to be x divided by 4 to power n. And I did forget one thing. There's a extra fraction, -1/4 in the front. Let me move that over real quick. This equals -1/4 times summation from 0 to infinity, -x over 4 power of n. Okay, I rewrote all that, but all I did was include that -1/4. Definitely don't forget anything you had to factor out as well. Oh, that was a mistake on that copy end. Thanks for spotting that. That should have just been positive x, everything to the right of that negative sign there. Other questions so far? Okay, so with those multiple corrections in mind, we're now ready to go on the next step. You know, honestly, if you stopped right here, that would be okay in my view, except that in 11.9 and the next section, 11.10, we are going further with these. We want to integrate them or differentiate them. And so sometimes we really want to go a little bit farther. So this next step for the simplification is really just a best practice for what we're really getting into beyond these notes. Let's rewrite this as -1/4, a sum from 0 to infinity, And let's break this apart. Raise x to the power of n in the numerator, 4 to the power of n in the denominator. Getting it separated like this is going to make it way easier to integrate and differentiate in the next sections. And we get a little bonus. You can now distribute 1 over 4 inside and bump that power up by 1. The negative sign still stays right here though. So this is negative sum from 0 up to infinity, x power of n, 4 to the power n plus 1. So this function f of x has domain all real numbers except for 4. And now this one, its power series representation, has a severely limited domain, but this is an interesting tool that's going to help us out a lot if we're integrating or differentiating functions later on in 11.11. Last thing we want to get is the interval convergence, but that just moves us into the so-called provided that part. What we're saying is this representation works on the domain specified this way. So notice the yellow highlighting. I'm going to try to maintain this through the notes all the way through. Our provided that is now this. We have a power series representation provided that this in absolute value is less than 1. So again, whatever takes the role of x, it goes over here in the power series raised to an nth power. Then we take that same x, set it in absolute value less than 1, and solve it to get your full interval of convergence. Kind of a lot of mental backflips to force it into that format. But once we're there, we have a power series. So we just need to do a little bit more manipulation with this. This is absolute value of x divided by 4, less than 1. Then just multiply both sides by 4. Absolute value of x less than 4. And this directly tells us interval of convergence is from -4 to +4, just coming out of that inequality there. If you pick any of the x's in this range, then an absolute value will be less than 4, which guarantees convergence now. Maybe one major comment to make. This is a power series once you get to this stage. And based off the problems we just did, you might be tempted to use something like ratio test on it to determine interval convergence. And that would work, you really could. But keep in mind that the formula gave us a huge way to simplify this even further. If you're using this formula up above, there is never a need to determine interval convergence through the ratio test. It's already provided directly through the geometric series test. So let's make a really strong comment right here, just as a reminder to help with homework and potentially with exams. Ratio test is not needed since the formula directly is a strong word here. The formula gives a shortcut. It's indirect. We had to do some algebra to get there, but it gives a major shortcut to this, the interval of convergence. So our starter problem, it's really more about the comments on how we analyze in this brand new way for this new kind of problem and the things you don't have to do. It's very tempting to hit it with the ratio test. We're really good at it. We've used it like a dozen times, but this is a good time to skip it outright. Well, we've got it, folks. That's our first one down. This is such a probably new and interesting way to do a power series representation that we ought to do a couple more examples just like this one. But any questions at all getting to the end on this one? Okay, so your function 1 over x minus 4 can be represented this way exactly, but on a limited domain. Notice what's interesting though, the size of this domain is the distance from 0 value, which is the center of that power series, to the first discontinuity of the function. That's not a coincidence. That's something we might observe in a lot of the problems once we get the power series down. And let's try it out again on this one. the observation breaks down. This one has no discontinuity whatsoever because f of x due to the power 2 never can produce a 0 in the denominator. Yet, if we use a power series representation, you have a domain which is all real numbers, which gets severely limited to whatever I turns out in this problem. But think of this as practice. We're doing all this work because sometimes along the course of solving problems like we saw in differential equations, we run into integrals we cannot integrate. So we need these kind of methods to do a good approximation. So steps on this one is, here's our first problem. We want a 1 in the numerator, but we've got a 3, so we just ditch the 3. Let's factor out a 3, and while we're at it, let's get our other 1 down below by also factoring out a 5 all at once. So removing 3/5 is going to take us to 3/5 times 1 over 1 plus x squared over 5. So we've satisfied those two requirements, the 1 and the 1. Other requirement we still need is a negative sign. But that's not so bad. You can always force a negative in the middle, just use double negation. So this is 3/5 times 1 over 1 minus x squared over 5. Once we do that, we have our negative right in the middle. And so the next thing we analyze is this part. Our x to the right of the negative sign, so let me grab that negative sign. To the right of that negative sign is this now. We do have an extra negative because of our double negation. And this x down below is playing the role of all of that information there. We take this x, gets fed into the power series in that kind of way. So we're going to do the same exact thing with this x. Just let's recall this time that we keep our 3/5 this fraction right in front. Now we take a summation from 0 to infinity of x power of n. That's what the formula says below. Our x is all of that, negative x squared over 5. So at this stage, we've got the power series. We're now just taking the steps of simplifying, finding its domain, the so-called interval convergence down here. Any questions to get to that key step up here? Okay, let's do the simplification part. There's really 3 different factors we're interested in: the -1, the x squared, and the 5. Let's distribute n across all 3 of those values to get 3/5 times sum from 0 to infinity of -1 power of n. We have an alternating part. X squared to the power of n is just x to the power of 2n. Those exponents would multiply together. Denominator is 5 power of n. That means we can grab this factor of 5 and combine it inside, make that a 5 power n plus 1. The 3, however, stays exactly where it is. It has no factor to combine with it. You could put it on the inside of the numerator. No harm done. But I think personally I would leave it just outside like this. Your choice. -1 power of n, x power 2n forms the numerator. It's divided now by 5 power n plus 1. So this is the format of 3 divided by 5x squared. Really bizarre looking function. And here's the last part for our domain. This works provided this part, negative x squared fifths, doesn't exceed 1 in absolute value. This is kind of an interesting one to analyze. When we go to take the absolute value of this, everything drops, including the negative sign, leaving behind just x squared fifths. So we have x squared fifths less than 1. We're getting there. Multiply both sides by 5. X squared less than 5. Now, we cite this formula a lot. It seems to sneak into the mathematics in a weird way. Here, we want to relate x squared down to x, so we want to take the square root. But if we take the square root at this stage, we have to recall that square root of x squared is absolute value of x, one of its interesting definitions. Square rooting both sides of this equation then would give us absolute value of x. That's why we don't need plus or minus anymore. It's already captured in the absolute value. Less than square root of 5. That's kind of interesting in a way. And if we broke this by eliminating the absolute value right here, we would be saying x less than root 5, bigger than negative root 5. Let me fix that square root symbol. This directly tells us, therefore, interval of convergence has to be parentheses on both ends. So negative root 5, positive root 5. But again, there's no further testing on this. The geometric series directly tells us divergence right when this is equal to 1 or greater than 1. So that's why we stop right here. We don't use the ratio test. We don't even test the boundary. That's the exact interval of convergence each and every time. And we didn't mention that in the last problem, and this is a easily thing to mix up using the ratio test here. So let's say it again. Diverges at the boundary. The boundary is the negative root 5, the positive root 5. Since it's known to diverge, no further testing is needed. Which is in a really stark contrast where if you did use a ratio test, you really do have to test the boundaries because the ratio test fails on the boundaries. But this geometric test here never fails on the boundaries. I was hoping for information that wasn't there when I scrolled up. It's based off of this geometric series test. Notice it gives total information for less than 1, greater than 1, as well as equals 1. Greater than equal 1 is divergence, and that's why we're happy with that right here. If we did use the ratio test, we would just be coming up with this same foregone conclusion. You would just find it diverges here and here. Well, any last questions, folks, on finalizing this one? Okay, these are weird problems because most of the writing is right over here. However, the tricky part of the problem is probably just that. It takes a little careful work on doing this each and every time because it's just unusual algebra. We probably never really want to factor out a 5 unless you're doing this kind of thing, including a double negative out of nowhere. It's just weird on the brain the first time you kind of do these steps. So we'll do them a whole bunch more times on these notes for extra practice. So here's the next one to try. Pretty much each time you do this, always you want to look into this formula. Let's look into our wants. We have a 1 here, which matches that 1, so that's good. We're on the right track with that. Next thing is, we do have the negative splitting the term in the middle, so that's even better. We don't have to factor from the denominator for the first time. Only thing that we need to deal with is forcing the numerator to be a 1. That's not so bad. Just take out 2x power 5. So 2x power 5 now multiplies 1 over 1 minus 2x squared. This gives us our right format. 1 is in the numerator. We have a 1 in the denominator as the first term. We have the negative sign. And now the 2x squared is going to play the role of that x there. Does that make sense to folks so far on what we mean by contortionistically taking f of x, forcing that format? Okay, so with that main idea, next thing we do is we take this x, which feeds into x power of n in the geometric series, and we're already looking right at it. It's the value to the right of the negative sign. So this time, 2x squared. Double negation wasn't required, so we're not pulling in the negative sign this time. We're just taking this as 2x power 5 multiplying a summation from 0 to infinity of something to power of n. And again, looking down here, the thing to power of n is whatever is to the right of the negative sign, which is at 2x squared. So all that directly just copies right in. Now we're on the step of simplify this by an interval of convergence. But these were the key steps we were mentioning earlier. These are the tricky steps. This one might not make it onto exam 3. We're not trying to race through the notes today to force it. But if this problem comes back on the final exam, and if this is, say, a 6-point problem, I'd say this is 4 out of the 6 points. You've got the representation. You're now just going for the domain. So let's simplify this further again. 2x power 5, a sum from 0 to infinity. Simplifying involves just breaking this up. Raise 2 to the power of n times x squared to the power of n. Again, those would multiply, so that's really x to the power of 2n. And that's a 5 there. Let me fix my formatting. That means this time all the coefficients in front can combine with what we have inside. So this is a sum from 0 to infinity of 2n to the power of one more factor times x to the power of 2n coming from here plus 5 more factors, so 2n plus 5. And finally, that's it. That's our power series. We take the next step to say, provided that this thing, 2x squared, is strictly less than 1 in absolute value. So that's this step right here. Whatever we threw into there, we double check by forcing it less than 1 in absolute value. Double check's not the right word. Investigate the interval by doing that step. Well, how would this one go? This one's even weirder because absolute value does nothing here. 2x squared is just purely positive. So we would get a new line that goes 2x squared less than 1. Divide by 2, x squared is less than 1/2. Let me clear off a little bit of space here. Next step, take the square root of both sides. Square rooting both sides will give us absolute value of x less than square root of 1 is 1, so square root of 2. And here you could break it up into a triple-sided inequality like we did in the last problem, but you don't necessarily have to. You could also just say that this implies interval of convergence is take a negative value first, negative 1 over root 2, up to the positive value, 1 over root 2. Then our work is complete on this one, folks. This highly unusual function can be rewritten in this worse way. And the domain, well, it's kind of small, but we've got a domain at least. There is a small set of numbers for which this actually makes sense, centered at right at 0. Well, that's 3 down. We're going to turn this around a little bit more and take a look into what other kind of functions we can represent in this way. But this is what fractions like this would look like. 1 term in the numerator and 2 terms in the denominator. Well, let's try a look into the next concepts then. First, any questions or comments with the last 3 problems we took a look into? Okay, so here's our next one to investigate. This looks a little bit rough though, the first time we take a look into it. And maybe before example 2, let's pause just on the notes here. Let's push that down and take a look at this statement. I mean, it's a huge statement. It's taken up about half the page. This is one of those theorems where our author says he's not going to prove it, but he needs it, so he threw it into the book. If you're taking elementary analysis, real analysis, you're probably going to get into the work that involves this kind of stuff. Here's how it goes. It says, if you have a power series written in this way, you can, in fact, integrate and differentiate your power series in a really interesting, sensible way. First, starts with a radius convergence R. It's got to be positive or infinity. We don't want equals 0 because nothing is exciting about that function. A function that has 1 point in its domain is not differentiable. It's just one discrete point all on its own. So that's why we're insisting a positive radius of convergence or an infinite one. Then we take this function, and now imagine you want to differentiate that thing. How would that go? Well, here's f prime of x like we would normally do. Here's d by dx. Here's where the magic happens. Before this theorem was rigorously proved, this was used as a formula, but it got extreme criticism. People were doing things like Fourier series without any mathematical backing of why it actually was true. It just seemed true, so people used it. The drama was taking something like a differential operator or an integration operator across infinitely many terms. This causes a logical kind of confounding that happens, but you really can do it. What happens now is that's the heart of the theorem. That if you're differentiating an infinite sum, you can take the sum of infinite derivatives, is what this is saying. Just differentiate all of the terms inside here. Very bizarre in a way. Now, when you go to differentiate, Cn is literally a constant. It's defined to be the coefficients of the power series, just a constant. That means you're differentiating x minus a power of n. That's just the ordinary power rule. So the differential operator, which is doing infinitely many differentiation operations, gives us power of n comes down right here, and that power is one less. But notice something else that's kind of interesting. This starts at 0, which puts a 0 there. So your very first term is just a constant, maybe like 1 or 3, something like that. So when you go to differentiate infinitely many terms and exactly 1, the first term is a constant, you now have to reindex. There is no first term. There's a one term, a second term, and so on down the line. So upon doing, sorry about that, upon doing the differentiation, f prime of x reindexes, well, really just starts the indexing at 1. Bizarre statement, right? And you can turn this around as well. If differentiation works, anti-differentiation should also work. So now we're looking into integration. Again, this was just pure drama back in the day, hundreds of years ago in the mathematical community, because people were doing this. They're integrating a function f of x, but you know, I kind of didn't put that in. Let's actually be a little bit more descriptive. It means if you're integrating f of x, you're integrating this. Let's write that in just to really highlight the interesting thing that happens. We're integrating in this way with respect to x. So this is an edit, just including it. The integral sign is now on the outside. So it's just saying integrate once, whatever this total sum comes out as. But people found easier to integrate that way, right? Integrate the infinitely many terms because we have a function or a formula for that. If we integrate here, power goes up by 1. We divide by the new power. So upon integration right here, Cn is a constant, so it's just moving in front. All we're really integrating is just that part. So that's why you see the n plus 1 power, n plus 1 down below. And you also see the constant of integration. We are still indexing at 0 because our first term doesn't vanish when we integrate, but we actually have an extra term. If we want to include that somehow, we would index at -1 to start with the first constant, and then at 0 for everything else. Way easier to just leave that constant of integration here because it's not necessarily going to fit into any pattern on the coefficients. By its nature, it's any real number whatsoever. So on one hand, it does make sense. If you integrate f of x, you get a constant, but you're also integrating this. So x minus a, the power of n, increases the power, and we divide by the power. So very bizarre stuff. I'm going to leave this part circled in just as a reminder. If you differentiate, indexing starts at 1. That's easy to forget. And let me also leave this part in as a reminder. I mean, we know this, but these methods are so weird that if you integrate a power series, we should have a reminder that you pick up an extra term at the same time. So that's 2/3 of the theorem. But the final 1/3 of the theorem that is really amazing is whatever you stated as a radius of convergence does not change. Same radius of convergence here, Same radius of convergence here. So you just find the radius once, and if you differentiate, cite the same radius, and same with integrating. It's kind of nice in a way. This is weird enough, we should practice immediately with it. Let's use this as a practice function. Let's call that our f of x. The radius of convergence is this part, 1 over root 2. So not a baked-in example, but definitely a good example we should try. Let's both integrate and differentiate this one. Let me, before I forget, cite radius of convergence, 1 over root 2. And let's also cite this as a literal function f of x. That's what the notes 11.9 are really all about. Regard your power series as a literal function now. Okay, let's start with the differentiation phase. But any questions at the moment with what we've got on paper so far? Okay, so if this is our f of x, it's a weird function, but the derivative is not as bad as it seems. It just needs a little bit of carefulness because it's the first time we've done this theorem. Derivative of f of x really looks like this, but for applying the theorem, I want to write it in that step right there. It's a sum from 0 to infinity of the integral of 2n plus 1 x to the power 2n plus 5 dx. Sorry, I got a little bit mixed up. We're differentiating, not integrating. I think I was looking on the wrong line here. Let me try one more time. We will do that problem, but we said f prime of x. Let's do what we actually said we're doing. D by dx of 2 power of n times x power 2n plus 5. Oh, absolutely. Thanks for spotting that. Having trouble with my exponents today, seems like. N plus 1. Okay, that's what it would look like to start. I'm still at 0 because we haven't differentiated just yet. But now upon differentiation, it's indexed now starting at a 1. That always deserves emphasis. That's really easy to miss, I would say. And we're also differentiating as normal. 2 to the power of n plus 1, that's constant, because this is d by dx, not d by dn. So this is just a built-up constant. But this varies. If it's d by dx, you're just differentiating that part right there. So let's write in 2 power of n plus 1. Derivative of x power 2n plus 5 is 2n plus 5, x to the power 2n plus 4, so 1 less. And our job is done. That's the derivative now. Pretty weird in a way. And as a bonus, if the radius of the original function was 1 over root 2, we don't have to do any further testing on this one. That's kind of merciful in a way. We just recite radius 1 over root 2. I'm making a big emphasis on this because if this was a final exam question, instructions would say, give the radius of convergence, state the radius of convergence, something like that. But just a big reminder, you don't need the ratio test to find it on this kind of a problem. Well, that's what differentiation looks like. Let's turn it over to integration, and then we'll see how these next kind of problems will go. So next one is integrate f of x dx. So it looks like this to start. You're integrating the result of the actual power series down here. But we'll move it over to this line. This is where the theorem itself begins. It's a sum from 0 to infinity of integrate 2n plus 1, 2 to the power n plus 1 times x to the power 2n plus 5 dx. So there's no constant on this step because we haven't integrated. We just indicated what we are integrating. And taking some parallelism from the line above, because the integral says dx, the only part that's variable is now x to that power. This part would be constant. So integrate. Don't forget the constant of integration because this feels like it's such a different problem. It really is easy to forget that part. So here's the constant pulled in, plus a summation at the same index start, 0 to infinity, because this part right here is constant, no change, 2n plus to the power n plus 1. Then integration is going to bump the power here up by 1. So this turns into x 2n plus 6. And then that informs us we have to divide by 2n plus 6. And our job is done. The antiderivative of that function as a power series looks like this. And even better, just like before, radius is still 1 over root 2. No change on radius, whether we differentiate or integrate. Pretty bizarre problem in a way, but any questions at all, folks, finalizing this one? Okay, so this theorem says a lot of stuff at once, and it says it in a way that's kind of overwhelming. There's a lot of information here, but this is another way to think of the theorem. In a concrete example, all the big wall of text that last theorem is trying to say is, if you differentiate this function, you're differentiating x power 2n plus 5, and you index start at 1. And if you integrate this function, you're just integrating x power 2n plus 5, and you'd have to remember to include the constant of integration. So that's the really short part of that theorem, including the extra information that this carries over in this way every single time. Not a coincidence, it's a pattern. Now we're going to apply that theorem in different ways throughout the rest of the remaining part of chapter 11. But the next goal of chapter 11 is to get representations of these kinds of functions as power series as well. Our original strategy of our example 1 to try to force it into this format doesn't work at the start. So we need to do something extra so that this formula does get pulled in. So let's capture this again. We're about to reuse it. And let's try it out next on example 2. We want a power series representation for natural log x squared plus 1, as well as its radius of convergence. But the function in no way fits this format. There's nothing I can do to make that work. However, here's a weird method that will work. Just differentiate the function. If you take this and go f prime of x, then the derivative of natural log x squared plus 1 drops x squared plus 1 into a denominator. I'll write it this way, 1 plus x squared, because we're going for that format. Chain rule says multiply by the derivative of 1 plus x squared, which is a 2x going up into the numerator. And now here's the interesting thing about this problem. The derivative does fit that formula. We can take some work, make the derivative look like that, then relate the power series representation of the derivative back to the original function. So this is a kind of a multi-pronged attack this time. And what supports this step is these ideas right above. We're going to have to eventually integrate that function, but we know we can do that in a sensible way now without changing radius of convergence whatsoever. So here's how it goes to start. This is a process, so let's call this step 1, differentiate. Then step 2 is everything we're going to do below, obtain the power series representation. Let's look into what we need. We need a 1 right here, so we've got that matched up. We're going to need a negative sign, and we're going to need a 1 up here. So we want to factor out a 2x, as well as put in double negation. 1 over 1 minus, that's singular negation, 1 over 1 minus x squared. So now looking into the format, we have the 1 down below, the negative sign, and so now the x that feeds into the power series is identified as being that portion just right there. So we'll do exactly that. Let's throw it into the power series. 2x still copies in. Sum from 0 to infinity. And we take x power of n, or x being, let me fix Microsoft for a bit, or x being that negative x squared. And now remember on the example one, parts A, B, and C, we were constantly saying, for doing more with this function, best practice is put it in its most simplified form by expanding out the power. This is the case where it actually matters because we're going to need to integrate this function. It absolutely matters that we put it in its most simplified format. So next step, let's say that this is equal to 2x, sum from 0 to infinity of -1 power of n, x to the power 2n. So we broke up the exponent n here. N is multiplying 2 to get the 2n. You still don't want to integrate this because now you're integrating x times a power series representation. And I can imagine no one wants integration by parts on this thing. So just take base x, combine it with that. It's now, I'll leave the 2 just hanging on the outside. Oh, and I forgot the 2 after saying that. There's the 2. 2 sum from 0 to infinity, -1 power of n, x to the power of 2n plus the one additional factor that we pulled in over here. Once we have that, we want the radius of convergence for this f of x as a power series, but we can get the radius of that convergence by finding the radius of convergence of just its derivative, because when we integrate, that radius does not change. So we don't want the interval of convergence like we were saying down here. It's asking for something new this time. It wants that part, radius. So just a little bit of fewer steps in the algebra is what this boils down to. So we'll take this, an absolute value, set it less than 1. It's going to simplify and feel like deja vu. This is now just x squared less than 1. Take the square root of both sides, and now it's absolute value of x less than square root of 1, which is 1. And this is radius of convergence. R is 1. Despite all the algebra we took, it never changed the value right here. But still, it's a good idea to bring it back to absolute value of x, because sometimes it does, depending on what's going on up here algebraically. At this stage, we're totally done with the geometric series test as stated here. But we need to take the function f prime of x, relate it back to f of x. So that's our new challenge right here. Here's the derivative f prime. But what we wanted was f of x itself. Actually, it's not too bad. Here's what you do on this step. It's confusing at first, but we have to remember if you integrate a derivative, you get back to the original function and an arbitrary constant that we have to solve for this time. So we can now write that f of x is the integral f of f prime of x dx. Now the theorem that we were just looking into is finally relevant because we're about to integrate infinitely many different terms all at once. It's impressive when you say it that way, and it really is exactly what we're doing. Just to emphasize, we're getting a representation of natural log x squared plus 1. I'm going to replace the f of x here and actually put in natural log of x squared plus 1 in its place. Then f prime of x comes in this way. I'm going to write it in as a 2, sum from 0 to infinity, -1 power of n. But then the integral sign that was right here moves right in front of the power of an on x. So then integrate x power 2n plus 1 dx. So that's how we go from the function related to its derivative, and the fact that the derivative is a power series just means integrate that part of the power series. So there we are on that line. We now need to write in natural log x squared plus 1 equals 2. No, before we put in that 2, let's back off one step. Recall, this is what we were mentioning earlier. Easy to forget that there is a constant c of integration once we conclude this integration step, which we're about to do. So we should throw that in just right away. It's going to be a constant c plus. Now, we can throw in the sum from 0 to infinity. -1 power of n Finally, right here, we integrate. Power goes up to power 2n plus 2. X power 2n plus 2. Divide by 2n plus 2. And next thing we can say, by again, that same powerful theorem says, the radius of convergence we just found is relevant here. Same exact radius of convergence. You didn't actually need to test this one for what its radius would be. It's inherited from this one. But we're not done though. We wanted a power series representation for natural log x squared plus 1. And we were really close. Here's natural log x squared plus 1. It has something solid right here. But c is a constant of integration. By its nature, it's any real number. You have to solve for the exact real number that satisfies natural log x squared plus 1. So there can't be a possibility of different numbers on c. We must solve for it. I gotta be honest though, oftentimes when I see these kind of problems, maybe it's the way the author writes out the textbook exercises, usually the constant is 0. It's not a guarantee, but it's an expectation on a lot of these. Here's what the steps looks like in solving for it. I want to pick a value for x based off what I see right here. There's one value I can pick that makes life easy. And as you said, exactly, think of the center is 0, pick x equals 0 each and every time you do this kind of problem. This deserves a pretty big comment since there's a lot going on right here. We're solving for c. To solve for c, find the center, A. And let's get another weird color. That's why we constantly mention what is the center of the power series in the last section, because it's relevant in surprising ways. Here, if this was x minus 3 to the power 2n plus 2, the center is positive 3. But now this is like x minus 0 to power 2n plus 2. Center is A set to 0. That means A is 0. So now let's connect that thought with what we're about to do to solve for c. Every time you go to solve for c and there's a power series somewhere, find the center, set x equals A on both sides. So the best x to pick is the x value that represents the center, A. In this problem, it's 0. So let's take that again. Running out of colors here, but we'll make it. The left-hand side is now natural log 0 squared plus 1 equals the constant c, this is the part that we're solving for, plus a sum from 0 to infinity. Some people might wonder why we write this in at all, only for the sake of clarity. We're also plugging 0 in right here, so it's times 0 to a power 2n plus 2, but it almost doesn't matter if we put 2n plus 2 on there, right? It's still 0. It's possibly more confusing to put it on there. It is divided by 2n plus 2 in the denominator, but the entire power series is just wiped out, converges to 0 exactly now. That means we have natural log 1 equals the constant c, but then that means 0 equals the constant c, since natural log 1 itself is 0. You really have to show those steps, but I've observed, like I mentioned before, it seems like somehow, some way, 0 is a common output here. Here's our overall conclusion. We can say, therefore, as a power series representation, well, natural log x squared plus 1 has a domain, all real numbers, but if we had any cause to work with it as a power series, we would write it out this way, where the red dot is here. That constant c we found to be 0, so we just say it's equal to sum from 0 to infinity, negative 1 power of n, x power 2n plus 2, 2n plus 2 down below, and radius, same as before. Radius equals exactly 1. Let's take a fuller view of this problem. Notice how weird this is. The function was really hard to relate to the geoseries, so we differentiate. Now we can relate it to a geometric series. but it's not the function we want. So we integrate that function, yet integration produces a constant. We have to take the center, so we can set the x value to 0 so that we can solve for the constant. And that means if you're really tracking the arrows here going left and right, this looks like some crazy cross-stitch pattern going left to right, connecting all these dots. This is a problem that's really hard to understand just by looking at it in totality. That's the value of the YouTube video. If you're looking at these notes and you feel like I have no clue what's going on, it's because you really need to see the steps stage by stage, step by step on how it all combines. But I think this one is a really good one to end on for today because the next one, slightly harder, but same exact strategy. We'll come back on Monday, review what the strategy looks like, take on the harder problem, which leads us into a bigger full-on mathematical application, sure, but now we can integrate some pretty nasty functions. That is not easy to integrate whatsoever. You might make trigonometric substitution work, but that's after an extreme amount of effort. We'll do it almost effortlessly in comparison. And that's another tough problem to integrate as well. So that's our main objective with power series, obtain better ways to integrate these without using something like trapezoid rule. Because these power series often converge way quicker than a trapezoid rule. But that's all I have for folks today. If you have any questions, I'll be happy to help out. Otherwise, we just crossed the 75-minute mark. So congratulations, try not to work too hard. We'll pick this up on week 13. Oh, and I forgot to mention, this also implies this section 11.9 can be a potential final exam question, but didn't quite make it to exam 3. Well, at least it's on the video. Thanks, you too.